Good afternoon, everybody. Let's get started with the class. For announcements, homework 5 is posted. That's not due until next week, though, but take a look at that. That's going to be on microcontroller topics. Lab 7 starts this week, so we will be working on taking your sensors and your sensor code and your sensor hardware and integrating that with the constant speed prop work that you did in prior labs. So we're going to start putting the bigger blocks together and getting that working in lab. So for the previous class, we talked about microcontroller pin configuration, and we talked about level shifting between different logic levels, different voltage levels, and we talked about analog to digital conversion and how that works and how you can apply that to different inputs of the microcontroller. So today we're going to continue with microcontroller topics. We're going to talk about timer peripherals, and we're also going to cover interrupts. And these are two topics that you're using in lab. You started working with them before we covered them in lecture, but you had template code. So now I think you'll get a bigger view of how they work and look at some of the details of that. Okay, so let's talk about microcontroller timer peripherals, also just called timers of the microcontroller. So timer peripherals or timers measure time between event inputs. Um, so that's one thing you can do with timers. They also can produce accurate delays for output events. So you can use timers to time input events, and you can use timers to produce output events that have to be timed. You can generate, for example, timed pulses. So if you have to produce a pulse every once in a while, microsecond, millisecond, second periods, you can do that with timers of a microcontroller. You can also produce pulse width modulated waveforms like you're doing in lab. So that's a common application that uses timers. You can also implement real-time clocks. So real-time clocks are what we traditionally think of as clocks. They tell time of day. So you could have a piece of software that uses the microcontroller timers to have events happen at certain times of day. You can also count events with timers, and those events might be inputs to a digital port pin. So you can use those timer peripherals as counters. You can also implement watchdog functions on the microcontrollers. So a watchdog in a microcontroller helps catch when a program froze or maybe something in hardware or software didn't work right, and the microcontroller just sort of stops working. And you really want to reset the microcontroller at that point. You could have the microcontroller reset itself with a watchdog function that periodically, if you don't so-called pet the dog, the microcontroller will reset. So that's another timer function. Timers are based on counters. Okay, counters are integer values that increment at a constant rate. They have a defined interval that you can define, and I'll show you how to do that. But they can be tied to a crystal oscillator or a precise time base. So you can make them increment very fast, like a microsecond period, or you could have them increment more slowly. But when you think timers, think binary counter, a counter that either increments or decrements. Timers run asynchronously and independently of the main program typically. So asynchronously means that as things happen in the program, the timer is running behind the scenes and it might be running on its own clock, maybe not even the processor clock. And events might be happening, or it may be timing events that that don't happen in sync with the way your program is running. And they run independently. They can run independently. So in the background, again, something is this counter is incrementing or decrementing, and it doesn't depend on the main program functioning. Let's talk about terminology used for timer peripherals. I always found this a little confusing, so I'd like to point it out. there's something called output compare. So for output compare, what you're doing is you're triggering an output. You're making an output happen based on a timestamp that is compared to the current time. And remember, a timestamp and the current time, they're both integers. The current time is a counter value, and the timestamp is just a binary number that's compared against that counter value. So you can trigger an output to do things like create pulse width modulated signals. You can create precisely timed pulses. You can trigger events using the timers. And that's called output compare when you're comparing a timestamp against the timer, the counter, and you're having an output triggered on that. And then there's input capture. Input capture records the time, and remember that's a counter value. It records the time of an event, and you can do things like capture when an event happened. You can measure frequency. You can measure pulse widths of an incoming square wave or incoming pulse. You can detect or capture the time between events. You can measure duty cycles, things like that. Okay, so there's an output function of timers and there's an input function of timers. Let's look at a block diagram of a typical timer peripheral. Now, if you look in a microcontroller's data sheet, they're all going to look a little different. Here, I've taken many of the architectures, tried to boil them down into one architecture, and this gives a good view of what you'll see in a data sheet when you look at a block diagram of a timer. Okay, so we have these inputs here, and two of these inputs I've got labeled as a time base. So these are accurate time bases. Those are clock signals. Clock signals are square waves with a precise frequency. Okay, so those go into the timer peripheral. You can also have an external input, meaning from maybe a pin of the microcontroller. And that can be another clock input that you have a different time base outside of the chip, or you could actually time not just regular square waves, but irregularly timed input events. Okay, so you can use that digital port input for that. Okay, those go into a multiplexer. So the multiplexer, this MUX, selects the input source. Okay, so that's what's going into the counter. And all of this, I should point out, this is all inside the microcontroller, okay, except for that input from the external digital port, but this is all inside the microcontroller. Okay, so then we come to this block called a prescaler. It's interesting. Yesterday I had a conversation with someone in this class about prescalers, and this is exactly what a prescaler does. It reduces the clock frequency by a factor of typically 2 to the n. So 2, 4, 8, 16, 32, 256, 1024. So oftentimes they work by reducing the clock frequency by a factor of 2 to the n. Okay, so the MUX selects the time base. The prescaler, if you had, let's say, I'm going to make this up, a 16 megahertz input clock signal coming in, you could divide that by 16 and get 1 megahertz out. Okay, that's what that does. It actually divides down the frequency. And here is the integer counter. So this integer counter increments or decrements, goes up or goes down. It's an integer value, and that happens on usually each edge of the input source. Okay, so that counter can often be set to either count up or count down, and possibly on rising or falling edges or both, depends on the peripheral. But on each edge, this counter is going to go up or down. And then there's this timer peripheral control block. So this block compares values, it sets values, and it gets values. So you could set the counter value. So you can set this integer counter with a number based on what you have in software. Or you can read the counter value. You can capture it. So you can get that counter value, and then you can send it to software. You could write values to registers that control the timer peripheral, or you can trigger output events. You can make things happen on external ports or make things happen in software. And you can also get input from the pins. Okay, so that's a peripheral control there. And then we have registers, digital ports, and interrupts. So the registers, they'll store values, or you can communicate values, or you can implement other actions like make a digital port change state, all based on what's happening with the timer, whether it hits a certain value or it reaches zero or it overflows, things like that. And I'll show you some examples of how you can create, for example, PWM signals or read timing events. So any microcontroller application that requires precise timing probably uses timer peripherals. Oftentimes in code that we're writing where we just need approximately a 1 second delay, something like that. You know, in the Arduino, in that code, you can put a delay of so many milliseconds. And there's some overhead there, and it may not be exactly 1,000 milliseconds to make a second delay in your loop, but it's probably close enough. If you really need precise timing, you'll probably use the timer peripherals. And you can get to those, and I'll show you, you can get to those using some low-level registers in the microcontroller or high-level statements in the language. Okay, so that's a look at what is inside the microcontroller and what it does at a block diagram level. Let's look at an example of generating a pulse width modulated waveform. Right? How does this work? How does the timer do this? So microcontrollers use timer peripherals for square wave generations at digital ports. So you can use timer peripherals to do this. You can do it other ways, but this is a good way to get an accurate frequency or an accurate accurately timed square wave or rectangular wave. So frequency, phase, and duty cycle of the square wave can be controlled with those timer parameters, right? So you have that timer control, peripheral control that sets different values in memory or in registers and controls the timer, and I'll show you some examples. So PWM signals are generated using frequency control and duty cycle control parameters. And those are parameters of the timer peripherals. So let's look at a plot of the timer, the counter value in the timer. So this is the integer value that's stored in the timer. And let's look at that value over time. And when I say time, I mean clock ticks, right? The edges of the clock waveform, or maybe a prescaled version of the clock waveform that is reduced in frequency. Okay, so let's look at how to generate PWM, and let's base that on this plot here. So there's a max value that can fit in that counter, right? You have so many bits, it might be 16 bits or 8 bits or whatever. But for a certain number of bits, you have a maximum value that you can store in the counter, right? When all the bits in the counter are 1. So let's just say over time, this counter is incrementing, right? I show the straight line here, but it should really be dots because I have integer values here, integer clock ticks and integer counter values. So it's increasing over time. And it keeps increasing until you do something or the microcontroller does something. Well, you can define a parameter called top. Now, this terminology is specific for the microcontroller I'm showing you here. I think this was one of the Arduino microcontrollers. You'll see some different terminology in different data sheets, but you could translate this as generally how these work. But you have this parameter called top. Okay, and so what happens when the counter hits this top value is the counter is going to be cleared to 0, right? So it counts up over time, hits that value, and the microcontroller peripheral just clears it to 0. So it goes back down to 0 here. And then the counter starts counting again. Nothing stops the clock ticks from incrementing the counter, and it goes up and it hits top again, and it goes back to 0. Okay, so these values keep doing this, right? Increment, 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 reset to 0, keep going down. So there's another parameter called CMP. You could call it compare. That's a programmable threshold for controlling a port value. Okay, so let's say you have comp CMP here. It's less than top. And then let's do a plot. Let's create a plot of the port value. So the port can be either 0 or 1, right? Binary 0 or 1. And let's also have the time axis here. Okay. So every time the counter equals 0, when you have the timer peripheral set up a certain way, we're going to set the port value, or the microcontroller is going to set the port value to a 1. Okay, so right back here, let's start all the way at the left. The counter value 0, the port value gets set to a 1. And it's going to stay at 1 until something else happens. Okay, that thing that happens is every time the counter equals the comp value, the compare value, we're going to clear the port value to 0. Okay, so right here, I've hit the CMP, the comp value, and the port value goes back to 0. Okay. Okay, and then this continues, right? So when the counter equals 0, the port value goes to 1. When the counter equals the comp value, the port value goes to 0. When the port value, right? Oh, I'm sorry. Wait. I neglected this. So I want to point this out in this description. So every time the uh, so we talked about this, when the top value equals the counter value, right? That's when the counter goes to 0, and at the same time, that's when the port value goes to 1. I wasn't clear about that. So you can see how you have this counter running, right? And you're using these this top value and this comp value to control what this waveform looks like at the digital port, right? And this is the PWM voltage on the port pin. So this is what's happening when you're running the PWM code in lab. Okay. The top value sets the PWM frequency, right? So if I wanted to like make this waveform have a shorter period, I could reduce that top value. If I wanted to have a longer period or lower frequency, I can increase that up until the max value. So you can control the frequency or the period with that top value. And then this comp value sets the duty cycle, because you can see whenever the counter hits comp, that's when the value goes low. So the duty cycle is changing, but not the frequency when you change that comp value. And so let's take a look at an example of changing that compare value to a lower duty cycle. Okay, so here's that plot. So I've just taken that comp value, went from some high value to some lower value. So the time that the output port is high is shorter, because, well, the counter reaches that comp value faster. So I didn't have to change the clock tick rate. I didn't have to change the frequency that's set by top. I just had to change the comp value to change the duty cycle. Okay. And now we've used this PWM voltage or signal to control motor speed, and you can control LED brightness, things like that. But one thing we haven't done in lab, but you should know, is that you can actually apply external filtering to the port output voltage. And you can use PWM waveforms to create analog waveforms. In other words, if you can vary a DC voltage using the duty cycle, then that means you could just slowly vary that DC voltage, maybe a little faster, and you can create an AC waveform. And there's certain restrictions on that, on timing, but you can create, with good filtering, a reasonable looking AC waveform using pulse width modulation, where you're modulating the duty cycle to change the voltage value of the AC signal. Okay, so this is all enabled by microcontroller timers. So this is one way to use or a couple ways to use microcontroller timers. Okay. All right, so you're doing this in lab for motor control. How about measuring frequency? You're actually measuring frequency when you're using your tachometer in lab, right? The code that's running on your microcontroller measuring not the frequency, well, the frequency of blade crossings, but also converting that to RPM of a propeller. So microcontrollers use these same timer peripherals to capture the time of an event. And these events can include a rising edge or a falling edge or even both. So typically what you're doing is you're applying a voltage to a digital port input, and then you're capturing the time of those events. And then those event times provide a way to calculate frequency, pulse widths, relative phases of, let's say, two different waveforms, two different square waves applied to a digital port. And you can time square waves or you can time individual pulses. Okay, so lots of capability here. And you can do things like capture the timing of the pulses from an infrared remote control transmitter. So you could actually take your infrared remote control for your television or any device that uses an IR remote control. It actually transmits pulses, and you could have a microcontroller capture the timing of those pulses and build a universal remote control that can control, let's say, anything in your house, even autonomously if you wanted to. You can sense optical detector outputs like those used for chronographs and other rapidly changing sensor outputs very accurately if you have an accurate time base into your timer. So for example, let's take a look at measuring the frequency of a periodic square wave applied to a digital input port. And let's calculate the frequency by measuring the time between rising edges of the input waveform. So here is the digital port, the voltage applied to the digital port. Okay, this is an input here. Here's the port value versus time. Okay, and then let's look at what happens to the counter value across time as well. Okay, so let's say this voltage, this pulse is applied to the digital port input. Okay, so that rising edge is going to reset the counter to 0. So I have to configure the peripheral, the timer peripheral, to do this. But I'm going to set it up so that that rising edge resets the counter to 0 based on the input. So that counter then, once it's reset, it keeps counting. So that's a integer value that counts over time based on the clock ticks coming in. And then I get another rising edge of the input. And so what's going to happen is I'm going to copy the counter value to a register and then restart the counter. Right? So I capture this value and then I restart the counter. So that counter value is going to be the time between rising edges. And well, it's an integer value, but you can tell by the rate of clock ticks what the time is in seconds. Okay, so then we continue on in time. The counter resets to 0, keeps climbing, and then you get another rising edge. Right? Capture that value. Okay, and then it keeps going. Right? So let's assume a regularly spaced, constant frequency square wave here. Okay, so with each rising edge, we're going to capture that value and restart the counter at 0. And that captured counter value provides the input waveform period in units of ticks of the counter clock. And then you convert the waveform period in units of ticks to period in seconds using the counter clock period. So you set up that counter clock period. And then you can convert to, well, units we use, convert to the waveform period in seconds and then convert that to hertz. Okay. And you could do like we're doing in lab, you can take multiple periods and average those periods if you have either noisy or jittery input waveforms. Okay. So that's an example of timing these events. The event is the rising edge of the digital port, and using that timing to calculate something like frequency. And in lab, you're using that frequency to calculate the RPM of a propeller using blade crossings. So that blade crossings are the events. Okay. Okay, so let's take a look at how the Arduino language supports timer peripherals. Right, so I showed you those register variables, right? The top and the count and the compare. So you can do that. You can look in the data sheet of the microcontroller and use those. But let me get to a little higher level, and let's use the Arduino language to simplify timer use. Okay, so these are functions that are built into the Arduino language. So delay pauses the program for an amount of time in milliseconds specified as the input argument. Okay, delay microseconds does the same thing, but in microseconds. Okay, micros actually returns the number of microseconds since the Arduino board was plugged in. Right, once it began running, actually the current program. Right, so once the program starts running, when you plug the Arduino board in, this counter starts incrementing, and you can get the count in units of microseconds. Okay, and oftentimes, the resolution isn't 1 microsecond. It might be like 4 microseconds or 8 microseconds. So you'll get a unit of microseconds out, but the resolution might be not as fine as 1 microsecond. Now, when you're timing microseconds, you're thinking you're incrementing a counter that may be 8 bits, 16 bits, 32 bits, whatever. But that number could roll over. In other words, when all the numbers in the counter become ones in binary, and you increment that by a value of 1, it resets back to 0. Okay, so this number in the Arduino in your board will go back to 0. It'll overflow after approximately 70 minutes. Okay, if you use the millis, this is the number of milliseconds since the Arduino board began running the current program. This number will overflow, go back to 0 after about 50 days. So if you have to not overflow and you're timing something for a few days or a few hours, you might want to use milliseconds if you don't need the microsecond timer resolution, because you only get 70 minutes before the micros overflows. But you could capture that in software, and you can account for the overflow. That's not a big deal. But if you don't need the micros resolution, you could use millis. Okay, analog, right? That actually creates the PWM signal on the specified pin. And the frequency depends on the specific processor when you use this Arduino function. So in lab where you're using analog, right? Okay, that's setting all those registers, those parameters behind the scenes, and it's a fixed frequency. There's a fixed frequency. You can control the duty cycle. Okay, some more I/O here. This tone function generates a square wave of a specified frequency with a 50% duty cycle. So that appears on a pin. No tone stops that signal. Pulse in returns the length of an input pulse in microseconds. So you can measure a pulse applied to a pin using this function. There's different ways to use that. And if you have a long pulse, there's this pulse in long that handles longer pulses. Okay. Okay, so the Arduino language significantly simplifies using timers. That's the upside. But the downside is not all of the timer peripheral capabilities are accessible. So using the Arduino language timing functions and the native microcontroller timing functions, timer functionality, using those simultaneously can cause conflicts in the timer peripheral, okay, or actually using the timers. So this means if you're going to use the Arduino functions, stick to the Arduino functions. If those aren't working for you, don't use the Arduino functions. Program the microcontroller timer peripheral settings at a low level. And those are accessible from the language, from the Arduino language. And if you are experiencing erratic or inconsistent results using the functions, then also try the native microcontroller timer functions. In fact, that's what I did for the code that you're using in lab. I'm actually just using the lower level functions. Okay, so these are useful for your projects going forward. I think this is one of the key peripherals to learn for a microcontroller. Okay, let's talk about interrupts. So this is a change of gears, but you're also using interrupts in lab to do useful things. So interrupts stop the main execution of the program, and they immediately run a special function when an event occurs. And remember, an event can be like a pin going high on a digital port or a timer expiring, something like that. Right? So if you have a signal from a sensor that changes the digital input port value, or you have a timer event, something happens, the counter rolls over, something like that, or hits a certain pre-programmed value, or there are other microcontroller state changes, that's usually called out in the data sheet, then that event can trigger or fire an interrupt. And when an interrupt is, I'll say fired or triggered or run, when the interrupt is triggered, there's a special function that runs. So after that event happens, this function called an interrupt service routine is called, sometimes called an interrupt handler. And it's the code that executes, it's the code that you write that executes when this event occurs. And then the main program resumes after that ISR function completes its execution. The main program resumes where it left off. Okay. So there's different language you'll hear used for interrupt service routines. You'll see sometimes the address of that ISR or the interrupt handler. Sometimes that address in memory of the program is called an interrupt vector. Okay, so if you see interrupt vector, it just means the address of the ISR. So let's take a look at an example, a plot over time to conceptually show how this works. So you turn on your microcontroller and the main program starts running. And it's running over time. And then some event occurs. And so what the microcontroller does is it immediately runs the interrupt service routine. And so that code runs. And once that function is done running, then the main program normal execution continues. And maybe you get another event and the ISR runs. The ISR is done, program continues. Another event, ISR runs again, right? And so that continues on. Okay, so you could do things like capture timer values, right? So in your code in lab, every time the blade crosses the infrared sensor, an interrupt happens and some light calculations are done to calculate the RPM. So these interrupts are useful for storing timing of events. So you can capture that counter if a timer's running in the background. Or you can respond immediately to an external event. Let's suppose you've just detected something from an accelerometer and you have to fire an airbag, something like that. Okay, or you can execute functions at specific intervals based on the timer peripheral, based on the counter. or you can capture external data upon arrival. So, for example, if you have data arriving, either just a raw data on a digital port input or like a serial port input, you could actually handle that data once it arrives. Like you press a key on the keyboard and something arrives at the microcontroller. That key press arrives at the microcontroller, and you can act on it right away. Right? So you can have an interrupt execute on that. There's some guidelines in ISRs. So these little red functions down here, to improve the chance of success of your ISR working and the rest of your program not being affected in terms of performance, you really want to minimize the time that the ISR takes to execute. So you don't want to like fire an interrupt service routine and then do a bunch of loops and wait for the user to input something, because the main program has stopped and bad things can happen. You want to avoid complex computations, which, well, can take a lot of time. And typically, if you do have complex computations or something that takes a lot of time, you want to pass values to the main program so that the main program can handle what you need to do that takes time. And also, you try to avoid calling other functions that take a lot of time. Or you try to not call blocking functions. Blocking functions are functions that just wait for something to happen, like a key press. Okay. So I think those are really, they're when I first learned about interrupts, they were kind of scary because your program is no longer linear. It's not just going through and maybe branching and maybe making decisions and running in a loop, but based on something that happens in the external environment, your program's execution gets interrupted, and that's why it's an interrupt. Something else happens, and so it's no longer straight linear thinking. So, but I'll tell you, once you start using them for applications where you need them, they're straightforward to use, and they're worthwhile putting in your toolbox for microcontroller capabilities. All right. So, we talked a bit about um, so writing software, but let's talk about writing software for these interrupts. So the Arduino language has functions to simplify the use of interrupts triggered by the digital pins. Again, you can go down to the low level memory, registers, settings in the microcontroller. You could set those, but I found the Arduino IDE, the Arduino language, has a pretty good library for handling them. So let's trigger an interrupt on each rising edge of a digital pin. Okay, let's suppose that you're applying a digital signal to pin 2 here as an input, and you want to have something happen. You want to have this LED change state. If it's off, turn on. If it's on, turn off. You want that LED to change state on each rising edge of pin 2, just as an example. So here's example code that will do that. And you can see, looks like Arduino code with the setup and the loop. Here's the ISR down here. So let's walk through this and see how this works. So here is where I've just defined a variable, an 8-bit value that defines the pin on which the rising edges will be detected. So pin 2, that's pin 2 over here. And then I'm going to set the LED state to an initial value. So you see it's going to be a byte LED state variable. I'm going to make it low and make it a 0. See this volatile keyword here? What that does is that tells the compiler, hey, this variable LED state might change unexpectedly. So don't count on it staying the same if the program doesn't change it. It might be something in the microcontroller like an interrupt that changes it. Okay, so we set up, we run the setup code. This is the one-time run code. So here's the pin mode. I'm going to set the LED pin to an output. I'm going to set the interrupt pin, pin 2, to an input. And then I'm going to do what's called in Arduino attach the interrupt. So I'm going to call a function that attaches a function. It defines what function will be run based on the interrupt. Okay, so this is the interrupt pin here, right? Pin 2. And this is the function that will be called when the interrupt occurs. This is the ISR, interrupt service routine. And I'm defining the interrupt to fire, to happen, on a rising edge. You could also define falling edge. It doesn't matter, but this example uses rising edge. Okay. And then the loop. Look at the loop. This is very simple. Digital write the LED state to the pin. So that LED is going to be, well, let's see, it's going to, start at the initial value. And this loop just runs. So it looks like it's an infinite loop that doesn't do anything. If you didn't have an interrupt service routine, this would just loop infinitely and this program wouldn't really do anything. It would just constantly write that one state to the LED. But we know that we have an interrupt. So when something happens, a rising edge on pin 2, the ISR is called. So I've just named this ISR change LED state, and it just looks like a regular function, right? So here I say, when this is called, I want the LED state to be, well, the opposite. That, exclamation point there means invert the LED state. So if it was one, make it a 0. If it was 0, make it a 1. So every time that ISR is called, all this does is change the LED state. So notice that's happening independently from the loop, right? This loop is running, it's not doing anything, and then we get a rising edge, LED state changes, and then in the loop, see this variable here changed. It went from 0 to 1 or 1 to 0. So now this write function is writing a different value, even though it's not changing in that loop code. Okay, so this is triggering an interrupt based on hardware input. You can also, on some boards, for some Arduino boards, you can interrupt on timers. Okay. But again, this is the Arduino language. You can actually access more advanced interrupt features using the microcontroller configuration registers directly. Okay. So just to remind you, general guidance for writing Arduino software. I wanted to point out, you'll hear these programs called sketches. I still call them programs. I rarely call them sketches, but they're called sketches. Makes it seem simpler. You won't see the main function. If you've ever done C programming, you're going to see the setup and the loop functions instead of main. Setup runs once, loop runs repeatedly. This is just review as we go along. You can call user-defined functions, right? And so the workflow that you're going through, you're installing the board. Make sure up here you set the board when you change to different boards with different, let's say, timer functionalities. You create your program, you write the instructions, you compile, you upload, and then you use the serial port monitor, right? So we've done that, right? But I wanted to kind of back up and talk a little bit about when you write the code in those functions. Let's talk about the data types or variables. So this is important. So here's an example. I have declared many different types of variables here, right? Variable 1, variable 2, variable 3 are all of different types. I have a char or a char, byte, unsigned char, Boolean, unsigned int, right? These are all different types that you can use. And here's what they mean. So a char or a char represents an integer, can store an integer 0 to 255. So it's an unsigned value. There's no negative values. Byte and unsigned char, they're all the same thing. Okay. Boolean is a true or false value, and it's typically 0 or 1, but we take 8 bits to store that anyway. We like to stay on byte boundaries often. Unsigned integer, 0 to 65,535. That's 2 to the 16 minus 1. This is a 16-bit value. A word is a 16-bit unsigned value. A short integer is a signed value, minus 32,768 to 32,767. Integer is the same thing. So short and an int in Arduino, in the one we're using, is the same. Here's a long integer. That's actually 32 bits, so you can store big values. This is unsigned long. Same number of bits, but no negative values. Okay, and then when you get to floating point values to store fractional values, you have float and double, and they're both 32 bits, so it doesn't matter. In this compiler for this microcontroller that we're using. Okay, so they're going to vary depending upon the compiler and microcontroller you're using. Okay, so these word sizes and these types, they depend on the type of microcontroller IC. So check the information on your specific microcontroller, and if you're using a completely different IDE then and compiler, check what data types are available. Now, one point of this is this, that when you're choosing data types, consider the memory that is used. So RAM is limited in microcontrollers. Remember, you may only have a few K, maybe a few hundred bytes, maybe, not that much in a microcontroller. We're so used to running MATLAB and defining everything as floats, or, you don't have to define in MATLAB, but in C on a PC, you could, use floats and things might run a little slower, but if you only need integers. But we have so much memory on PCs, typically, we don't worry about it. But in microcontrollers, especially when you're using arrays, so if you have to store 100 values, would you rather use 100 bytes, right, if you have an 8-bit word, or 400 bytes with a 32-bit word? So you can really eat up memory if you have arrays of data types when you don't need that large range. And floating point math is often slower. So if you have to run a fast program, you have to do some fast calculations, and you can stick to integers, then there's often ways to use integers to do faster math. All right. Let's talk about some of the code that you can leverage in libraries. So the Arduino environment can be extended using libraries. They provide extra functionality for working with hardware, for manipulating data stored in memory, and other functions. Some examples are you can connect to an inertial measurement unit, a 3D accelerometer, a gyroscope, magnetometer to sense the Earth's magnetic field. If you want to make a compass, there are libraries that support this. Here's a library that supports that. If you want to use a display, attach a display to your Arduino, then, well, here you go, right? There's a library right here for this display. There are some common library categories for communications and data processing and data storage if you want some external memory, device control, displays, sensors, right? So timing, so lots of different libraries. I recommend, if you have something in mind before you go write it, search the web for something that might already be written. And then you can just import the library using one of the drop-down menus. And some of the libraries are installed with the IDE, but some may need to be downloaded. And you can see some common libraries here. Right, here's a website. There's some common libraries, but you can also go to GitHub or other sources on the web to find libraries. And there's tons of stuff out there. So if you're looking to do something, it might be written already. So do a search on a library and then put them together in your own custom code. Okay. So this is going to end our microcontroller discussion in this course. So I want to give some takeaways. So we covered the hardware options for various processors and development boards. So you can select the board and the processor based on the capabilities you need. We talked about peripherals, ADCs, digital ports, timers, interrupts, things like that. So when you go and look for a microcontroller, you might want to consider, well, does it have the capabilities that you need? And is the board the size you need? And does it take the power that you need? Digital ports for digital input and output are commonly used. So select a board with the right number of ports. We talked about ADCs, analog to digital converters, to take analog input, and timers for producing analog outputs like PWM or for capturing event times. And we talked about interrupts to asynchronously respond to events and have things happen on certain events. We talked about writing software really throughout the whole part of the course. I want to encourage you to explore more topics that we don't have time for in this course. For example, writing C and C++ for non-Arduino platforms, right? It's likely that if you go work somewhere or do some research, you might not be using an Arduino, right? You might be using another microcontroller. So I encourage you to take a look at non-Arduino platforms. Also look at data communications between devices like SPI and I2C and UART. I encourage you to look at some microcontrollers with the capability of debugging peripherals, so you can look at your code and watch it run, and analog comparators built in for comparing voltages and having things happen, triggering events, and also external modules and peripherals for communications and control and co-processing. So lots of different modules you can connect. Okay, so those are microcontrollers. And I'd also say, take a look at microprocessors. So take a look at the Raspberry Pi if you're interested in this topic. And there are other single board computers that are easy to use. This is a pretty common one. And this is more like a PC with some general purpose IO, right? You don't use this exactly like a microcontroller, but it does have general purpose IO. And it runs an operating system like Linux. So you can run Linux on this, a version of Linux, a distribution of Linux. They're usually smaller, lower cost, more portable, lower power than a PC if you have an embedded application. And when you run Linux, it's you can write some more advanced programs using some of the capabilities of Linux. Okay? And you can write in C++ or Python or any supported language. Right? So they typically have a lot more memory. You're not talking about K of memory. You might be talking about gig of memory. They have a faster processor for doing computations typically, although you might be able to time some more precise events with microcontrollers. But overall, if you have to do a lot of processing and less sensing and controlling, you might want to use a microcontroller, or I'm sorry, a microprocessor like the Raspberry Pi or other SBCs, single board computers. Okay, so I've gone a little over time here, but just in closing, check out homework 5. It is posted and it is due next week. Check out Canvas for all of the upcoming schedule events. I will hold office hours right after this lecture, so if you'd like to stop on by, stay on this call. If not, I'll see you next time. Have a great night.